Assalamualaikum and greetings to the respected lecturers of Integrated Design Project 2, Session 1, 2021-2022. I'm Nurul Syazwani binti Samri. I'm from Group K16. I'm in charge in Geotechnical Department with my fellow members Aisyah binti Saghafar. In the geotechnical design, the project is prepared for the purpose of a foundation design of a development project which is a 3-story bungalow located at Mukim Pulai, Johor Bahru, Johor. This project was provided with a soil borehole data, bearing capacity of the soil and some other parameters. It also includes the explanations of the final results of a geotechnical site investigation, shallow foundation and also deep foundation. So the scope of work in this department is number 1, establishing a soil profile and soil parameter. Number 2, design shallow foundation. Number 3, design pile foundation. And number 4, check the settlement. So the first one is soil profile. Soil profile is drawn based on categorization of both soil types, which is clay or sand, and soil consistency. So the soil is assumed as homogeneous, where silty sand means sand, and silt is assumed to be the cohesive type of soil as clay. Sandy soil possesses consistency from very loose to very dense, while clayey soil possesses consistency from very soft to very stiff. Soil profile across 3 boreholes, borehole 4, borehole 5 and borehole 5A is as shown in the diagram. So the next one is characteristic of soil parameter. So soil parameter, which include internal friction angle, cohesion, unit weight, initial void ratio, and compression index, are determined based on the SPTN value from soil investigation. These values are calculated based on equation that show correlation to SPTN value. Other parameters like saturated density are also determined using the table shown, where it is a penetration resistance and soil properties on the basis of SPTN number. Bulk density or gamma bulk also were determined based on the typical values of soil index properties in the table shown, where it stated the soil type and the soil consistency based on the SPTN number. So this is the summary of soil parameter for borehole 4, borehole 5 and borehole 5A. Next is number 2, which is shallow foundation. So it is often called footings, which are situated beneath the lowest part of the structure, and it is the first constructed element of a structure which is built after excavating the ground. And the function of shallow foundation is to transmit load from superstructure to the substructure, and in addition, the ultimate bearing capacity is defined as the smallest pressure that can cause shear failure to soil supporting the foundation. So this is the overview for the foundation that lies in the soil layer at borehole 4, borehole 5 and borehole 5A. So as we can see, the type of soil inside the borehole 4 and borehole 5 is the same, which is sand. Meanwhile, inside the borehole 5A, it is a clay. So in the shallow foundation design, Mayhoff's general equation of ultimate bearing capacity will be used in this design project. The equation is expressed as in this slide, where C is the cohesion of soil, Q is the overburden stress at base footing, gamma is the unit weight of soil, the F is depth of the footing, and NC and Q and gamma is the bearing capacity factor, and the other is the shape factor, depth factor and inclination factor. So the Mayhoff general equation is divided into a series of equations, where it is a shape factor, depth factor for df over b more than 1 or less than 1, and also inclination factor. So next is the example of calculation. So we take borehole 5 as the sample calculation at depth 3 meter to determine the bearing capacity in shallow foundation. So there is few assumptions has been made, such as the applied load is assumed 2000 kilonewton, and the dimension of the foundation is 1 meter times 1 meter and also 2 meter times 2 meter. So first, we calculate the stress at base footing, which is Q equal to gamma dF. dF is the depth of footing which is assumed as 1 meter. So after substitute all the value, we get the Q value that we'll use into the Mayhoff general equation. Others value also been calculated, such as shape factors, depth factors where the F over B is less than 1, and also inclination factor where this value will be substituted into the Mayhoff general equation to obtain the ultimate bearing capacity. Next, we continue calculate the allowable bearing capacity, the allowable load, the net ultimate bearing capacity, and also the net allowable bearing capacity. Since the applied inclined load is 2000 kN, which is greater than the net allowable load that we obtained, 228 kN, hence the 1 meter times 1 meter in shallow foundation is unable to support the column. So this is the summary of shallow foundation borehole 4. As we can see, for both dimension of foundation, 1 meter times 1 meter and also 2 meter times 2 meter, both are failed because the net allowable load for both dimension is smaller than the applied load 2000 kN. Therefore, borehole 4 is not suitable and inadequate in designing shallow foundation. Same goes to shallow foundation in borehole 5. Both are failed, so borehole 5 is not suitable in designing shallow foundation. But for shallow foundation borehole 5A, for dimension of 2 meter times 2 meter, we obtain the value of Q net allowable is 4179.61 kN, which is more and greater than 2000 kN. So it is considered pass and suitable and adequate in designing shallow foundation. The third scope of work is pile foundation. So pile foundation is described as a series of columns erected or put into the ground with the purpose of transmitting loads to a lower subsurface level. So it is used when a layer of poor soil is present at the surface. The pile distributes the building's burden to the earth through friction. So in this design, a driven pile will be used. The design criteria is divided into two types, which is single pile design and group pile design. The equation of static formula used to determine the geotechnical capacity of pile for single pile, where QU equal to the ultimate load, QB is the end bearing, QS is the shaft resistance. Next, the group pile. So the equation of the group pile is acting as block pile. So different calculation for different type of soil. So this is the sample calculation group pile for soil type sand and soil type clay. So in this part, we will calculate the suitable number of pile that can support the load at the termination depth. So we have assumed the termination depth is 20 meter. So taking the value of the Q allowable at termination depth 20 from the single pile calculation before, which is 648.4 kN, we will calculate the number of pile by dividing the Q vertical, which is 2000 kN, divided by the Q allowable, 648.4 kN. Thus, we obtain 3 as the number of pile. For a further consideration, we take 4 as the number of pile that we use to design the pile foundations. This is the summary of group pile foundation calculation. So the red highlighted indicates the data calculated at the termination depth of 20 meter. It also indicates the value of Q allowable that greater than the maximum compressive load of 2000 kN that we assume. So as we can see, started from the termination depth of 20 meter until the end of the soil layer inside the borehole 4, we obtain the value of Q allowable greater than maximum compressive load. So for borehole 4, it is suitable and adequate to design using group pile foundation. The fourth job scope is settlement. So we must check the settlement of the borehole foundation in order to identify it is able to support the load from the structure buildings or not. So the first one is settlement of shallow foundation. So there is two equation for settlement, which is number one is elastic settlement and number two is consolidation settlement. So for elastic settlement in the sand, the equation is expressed as shown, where B equal to width of footing, Q net is the net pressure from footing, ES is the modulus elasticity of soil. There is also Poisson's ratio of soil, and also the factors depend on footing flexibility. The number two is consolidation settlement, where it is applied for clay layer only. So the equation is expressed as shown, where CC is compression index, H naught is thickness of consolidation layer, equal to clay layer, and there is also initial void ratio of the consolidating layer, effective vertical stress at midplane of the consolidating layer, and also the increase in stress at midplane of the consolidating layer using 2:1 ratio method. Taking ball 5A as the sample of calculation, since the foundation lies at clay layer. So first we calculate the elastic settlement, and we obtain the value of 244.84 mm. Since the termination depth lies at the clay layer, therefore there is a consolidation settlement in the foundation. So we calculate the settlement consolidation by substitute all the value, and next we calculate the total settlement by adding the value of elastic settlement and consolidation settlement. So we obtain the value of 245.8 mm. Since the total settlement is greater than the maximum allowable settlement of 50 mm, shallow foundation is not suitable for this design. So this is the summary of settlement for shallow foundation. As we can see, for both dimension 1 meter times 1 meter and 2 meter times 2 meter, in all borehole 4, borehole 5 and borehole 5A, it shows that the settlement is not okay, indicates that the value we obtain is greater than the value of the maximum settlement of 50 mm. So we can conclude that shallow foundation is not suitable and inadequate in this design. So next is the elastic settlement for a single pile. Total settlement of a pile under a vertical working load Q is given by the equation shown, where there is three set of settlement calculated. Number one is settlement of pile shaft. Number two is settlement of pile caused by the load of pile tip. And number three is the settlement of pile caused by the load transmitted along the pile shaft. So by adding these three separated settlement, we will obtain the value of the settlement of the single pile. By taking borehole 4 at the sample calculation at the termination depth of 20 meter, so we will obtain the total settlement by adding the three value of settlement at different parts. Since below the foundation there is no clay layer, so consolidation settlement is not included. Thus, the elastic settlement that we obtain is less than the maximum settlement limit of 50 mm. Hence, the single pile foundation is suitable for this design. Next, the group pile settlement is expressed as given, where BG is the width of pile group and SE is the individual pile settlement. Also, by taking the borehole 4 at depth 20 meter as an example of calculation, we will obtain the value of settlement equal to 17.86 mm. So since below the foundation there is no clay layer, so consolidation settlement is not included. Pile settlement is within the limits, thus the group pile is suitable for the foundation of the building. The tables show the summary of settlement pile foundation for single pile and group pile. So for both analyses, we obtain the value that below the maximum settlement limit of 50 mm. So we can conclude that both design, group pile and single pile, is suitable and adequate for the design. So for the conclusion, shallow foundation is not recommended to use in this design. It can be concluded that reinforced concrete pile foundation with a proposed line and diameter of 20 meter and 2 meter respectively is suitable and safe to be used in the construction, as the design analysis is within acceptable requirements. That's all from me. Thank you.